When last we met, I had described for the very first time the notion of energy, suggesting in a rather dramatic way that the energy is a number that I can calculate that has the remarkable property that it remains unchanged or changes predictably no matter what occurs. And I thought that it was probably really important to get busy learning how to calculate this number. And so I derived the kinetic energy, the energy associated with motion, the first energy that we learned. And I discovered it's really easy to calculate the kinetic energy. It's 1/2 the mass multiplied by the speed squared. It's a scalar, not a vector. It doesn't have components. The mass in kilograms, the speed in meters per second, the energy measured in joules. And when I derived it, I finished with an equation that I'm going to begin with this time. So it was a kind of continuity. I had a rather mysterious equation that said that F parallel multiplied by delta x is equal to 1/2 the mass multiplied by the speed squared, the final speed squared, minus 1/2 the mass times the initial speed squared. And I identified that quantity, 1/2 mv squared, as the kinetic energy. I worked out its units and talked about how I might calculate it. That was the right-hand side of this equation, and I left the left-hand side of the equation a mystery. It's a curious thing that I've written here. The parallel component of the force multiplied by the displacement. I said nothing about that. And so it's time for me today to clarify what's happening here on the left-hand side. The question that I had originally asked was, what is the effect that a force has when it acts through space? I already understand the effect of forces acting in time. That's Newton's second law. F is equal to ma, where a is delta v, the change that I'm interested in, divided by the time in which that change takes place. So I already understand the influence of forces in time. I'm interested in the influence of forces in space. So I went a little crazy and multiplied both sides of the equation by displacement, delta x, which is the change of the position of the object in space. But what does this mean on this left-hand side of the equation, the parallel component of the force multiplied by the displacement? Well, first, the reason why I'm using the parallel component is that I realized that the component of the force that is perpendicular to the displacement does not act in a way that it could increase or decrease the speed of an object. It does not act in a way that could increase or decrease the motion of an object. All the perpendicular component does is potentially change the direction of the velocity vector, not change its speed. So the reason why I'm using the parallel component of the force is because I only want the part of the force that could actually change the speed and therefore change the kinetic energy. I multiply it by the displacement because I allow that force to influence the system not for a particular amount of time, but for a particular amount of space. This quantity appearing on the left-hand side of this relationship is called work. I've said many times in our discussions that there are terms that we use in everyday life, colloquial terms, that appear in physics, and I have to adjust the way that I think about them. Work is certainly a very common term. In our everyday lives, work means to engage in activities that have monetary value in exchange. I'm working right now because this is my job. This is how I earn my living. This is not work in the scientific sense. Work in the scientific sense is defined this way. The work done, which I'm going to use the symbol capital W. You may recall that earlier in our course I said the weight of an object is the force of gravity, but I said that I wouldn't use capital W as the symbol for weight because I had a better use for capital W in the future. Well, here we are in the future. Look, time travel. Here we are, capital W, the work. Now the units of work, well, I'll write it just right here again for the sake of completeness, is F parallel multiplied by the displacement. The units of this new quantity work are clearly the force in newtons times the displacement in meters. So a very, very suitable unit for work would be the Newton meter. But if I recall that a Newton is a kilogram meter per second squared, and I multiply that by a meter, I realize that a Newton meter is a kilogram meter squared per second squared. A Newton meter is fully equivalent to a joule. But what does work mean? Well, now I look again to the right-hand side of my equation and realize that the answer to the question, what is the effect that a force has when it acts through space, is that it changes the kinetic energy. Work is the manner in which forces change the kinetic energy of a physical system. Because if I look at the right-hand side of my equation here, 1/2 mv squared minus 1/2 mv naught squared, this quantity, 1/2 mv squared, is the final kinetic energy, so I can call that K, minus this quantity, which is the initial kinetic energy, I'll call that K naught. And so K minus K naught is a change quantity, just like displacement, just like change in velocity, just like every change quantity that I encounter in science. So K minus K naught, I'll call delta K the change in kinetic energy. And therefore, I'm going to write the work as being equal to the change in kinetic energy. This is a significant moment in our physics because I've just revealed the work-energy theorem. If I want to understand the meaning of work, I don't have to look any further than this equation. A force can act on a system through space in such a way to increase the kinetic energy. When the kinetic energy increases, delta X is positive. A force can do positive work increasing the kinetic energy. It's also possible that a force could be exerted in such a way that it decreases the kinetic energy. When you decrease the kinetic energy, delta K is negative. You've done negative work. When a force acts to increase the kinetic energy, it does positive work. When a force acts to decrease kinetic energy, it does negative. It's just that simple. A little detail that we have that's important to remember is that forces that are perpendicular to the displacement cannot increase the speed. They cannot decrease the speed. Since forces that are perpendicular can't affect the speed, they can't change the kinetic energy. And so an important idea that is really worth writing down is that perpendicular forces do no work. That very simple idea that perpendicular forces do no work, that very simple idea is going to be extraordinarily useful when I try to use the work-energy theorem to solve problems. Before I get busy solving problems, I'd like to make another observation about the work-energy theorem and how it sort of behaves. Imagine if I make a graph, and I've certainly asserted strongly earlier in the course that making graphs of physical quantities is a very good way to visualize what's going on. But imagine I make a graph of the force, I suppose I could say the parallel component of the force, but I should say the force, as a function of the displacement delta x. And this force, I'm just going to imagine some general force, very non-specific. Imagine that the force as a function of displacement goes this way, just a weird shape there. I would suggest to you that you have not solved a problem with this kind of force at all. Every problem that you've solved, the forces have been constant in magnitude. Here's a force that's crazy. It changes its magnitude as it goes. The reason why you've only studied forces of constant magnitude is because to do otherwise requires calculus. In fact, some of our friends in the audience who have already had an inkling of calculus will not be surprised when I say the following. If I compute the area between the force graph and the delta x axis, this area here, if I compute that area, I find that that area is equal to, effectively, force times distance. I have a certain amount of force on the y-axis. I have displacement on the x-axis. So the area under the force displacement graph is work. And that is a familiar concept. The reason why it's familiar is back when we did kinematics, I made a graph of velocity as a function of time. And I suggested that there were two facts about that graph that were useful to know. One was that the slope of the velocity time graph is acceleration. Okay, fine. But the other was that the area under the velocity time graph is displacement. So I was able to use a velocity time graph to calculate displacement. And as it happens, many other things. And I practiced. Well, now I realize, according to my definition, that the area under the force as a function of displacement graph is work. So I'll demonstrate now the application of the work-energy theorem to a solution to solve a problem that we've solved before, a problem we already know how to solve, a problem that was demonstrated to have a solution, the application of Newton's second law. Well, it's a good reason to use it as my first work-energy theorem example. It's something that's already familiar. Consider I have a horizontal surface here that is rough, so there's going to be some friction, and I have a crate. There's always a crate, isn't there? And then here's Slim, and Slim is going to pull the crate along the floor using a rope that's inclined at an angle. You may recall, you look back in your notes, is a problem that we solved by applying Newton's second law. In Newton's second law, or when you're using the techniques of Newton's second law to solve a problem, it's typical to draw free body diagrams. When I'm solving work energy problems, I'm not, in general, going to draw a free body diagram, but understanding the way the free body diagram works is often very helpful. So sometimes when I'm solving a problem, I'll see the free body diagram in my mind and use it as a reference, but I typically don't draw one. Here, I'm going to draw the free body diagram just for instructional purposes, because I'm going to have to calculate some work, and so I'll need to be aware of the forces and how they act. So drawing a free body diagram for the crate here, I'll draw its weight, mg, directed downward. There's a normal force, N, directed upward. In principle, some friction force, which opposes the motion, and Slim pulling with a force that today I'm going to call F, directed at an angle relative to the horizontal. Well, when I was applying Newton's second law to this situation, I wasn't very happy with the fact that the force F is directed at an angle, because my application of Newton's second law required that I examine the acceleration along the x-axis and acceleration along the y-axis. So it was appropriate for me to resolve the force into its components. When I'm applying the work-energy theorem, I similarly have a concern about this force being at an angle, because the displacement of the crate is horizontal along the surface, parallel to the floor. And so this force that Slim pulls with has two components. It has a component that is parallel to the floor that does work, but it also has a component perpendicular to the floor that does no work. And so I'll redraw the free body diagram again, except this time I'll draw it with the forces decomposed. I know that you've seen all of this before, but I think it's worthwhile to do it as a little refresher, because when you start using the work-energy theorem to solve problems, you will once again find yourself taking the components of forces. So here I've drawn the weight downward, and now I'll decompose this pull force that Slim exerts into two components. An F cosine theta component that is parallel to the floor. You know it's the cosine theta component because it's the component that's adjacent to the angle, and adjacent is cosine. The component of the force perpendicular, which is directed upward, and the normal force and the friction force are still well behaved, and there they appear. So this is my free body diagram. Yes, I could go ahead now and write Newton's second law for the y-axis, the x-axis, solve it out algebraically, and get any answer that you like. Any answer that you like. But this time, I'm going to apply the work-energy theorem, which says that the work done is equal to the change in kinetic energy. It's very compact, but very sophisticated. When I apply Newton's second law, on the left-hand side of the equation, it says sigma F, because Newton appreciates that it is the net force, the sum total of all forces, that is the cause of the acceleration. When I apply the work-energy theorem, I have to appreciate that on the left-hand side of the equation, the work that appears there is the work done by all forces that act. That when there's more than one force acting, naturally, there'll be more than one work, because any force that acts at least has the potential to change the kinetic energy of the object. But when I devised my definition of work, I had a little caveat there that said that perpendicular forces, that is, forces that act perpendicular to the displacement, do no work. Quick quiz. How much work is done by the normal force in this problem? 0. How much work is done by the weight force in this problem? None, although we will find out that when an object moves vertically, gravity does do work. But in this problem, the gravitational force is perpendicular to displacement and therefore does no work. And there is a part of Slim's force directed upward that is F sine theta. How much work does it do? None, because perpendicular forces do no work. Because perpendicular forces do no work, there are only two forces on this diagram that do work. So when I write my work-energy theorem, what I actually mean is that the work done is the work done by the pull force plus the work done by the friction force, and it is these two forces that change the kinetic energy. It is these two forces that change the kinetic energy? Well, I have to calculate those works, and so I will. The work done by Slim's pull force, WF, is the parallel component of Slim's force multiplied by delta x. Well, I have to be careful there. That's going to be F times the cosine of theta multiplied by delta x. That's how I would calculate how much work. And when I calculate it, it will be a positive quantity of work. Because notice that the force that Slim exerts, F cosine theta, is in the direction of the displacement, and therefore would act to increase the speed, therefore would act to increase the kinetic energy, which would result in a change in kinetic energy that would be positive. Slim does positive work. He's trying to put kinetic energy in. How much work is done by friction? How much work is done by friction? Well, it'll be the force of friction, which points in the negative direction. So I'm going to write negative the force of friction. Of course, I could take this further in my problem solving, realizing naturally that the friction force is the coefficient of friction mu multiplied by the normal force. Figure out what the normal force is, figure out how many newtons that is. But that's not my interest right now. That's more of a Newton's second law concern. That friction force, negative F, multiplied by the displacement delta x will be equal to the work done by friction. It's negative because the force of friction is opposite the displacement. Now in your mind you might think, well Shadi, it's just negative because it points in the negative direction. That's not terribly dangerous to do that because I'm usually going to choose my coordinates so that the positive direction is the direction the thing's moving. Typically that's going to happen. So it's okay, I guess, in a general sort of way, to imagine that the work is negative because the friction force is negative. But more importantly, the work done by the friction force is negative because the friction force acts opposite the direction of motion, and therefore, acting on its own, the friction force would reduce the speed. By reducing the speed, reduce the kinetic energy. By reducing the kinetic energy, create a negative change in kinetic energy. The friction does negative work. So what I have going on in my problem solution is that if the work done by Slim is equal to the negative work done by friction, the kinetic energy won't change because Slim is putting energy in and the friction is taking it right back out again. And so the energy of the object does not change. But if Slim does more work than friction does, then Slim puts more energy in than the friction takes out and the energy increases. But if Slim does less work than friction does, then the change in kinetic energy is negative. The object is going to slow down. This solution that I've done here, Charlie, you haven't solved anything, did you? There's no numbers in the problem. There's no numbers, so I can't calculate what the speed is. This solution that I've done is absolutely equivalent to the same solution that I would do with Newton's second law. They're equivalent one to the other. Now, from time to time, it may happen in your education where a teacher teaches you to do a thing the hard way and then teaches you to do it the easy way, and you get a little upset about that. Say, why not teach me to do it the easy way first? That's not what's happening. In this case, I've solved a familiar problem that is easily solved with Newton's second law. And I've solved it equivalently using the work-energy theorem. That's not a surprise. Where did my work-energy theorem come from? It came from Newton's second law. What's going to happen, though? When I evolve my understanding of energy, I'm going to be able to easily solve problems that are difficult or impossible to solve with Newton's second law. So, although we may not realize it at this point, energy is the better way to solve problems when you can. Not only that, a thing that you do not realize is that you've been using the work-energy theorem the whole time. Allow me to demonstrate. The work-energy theorem tells me that the work done is equal to the change in the kinetic energy. That is the work-energy theorem. Let me flesh it out. The work is the parallel force, F parallel, multiplied by the displacement, delta x, would then be equal to 1/2 the mass times the speed squared, which is the final kinetic energy, minus 1/2 the mass times the initial speed squared, which is the initial kinetic energy. On the right-hand side of this equation, let me factor out the 1/2 and the mass. So this is 1/2 the mass multiplied by the quantity, the final speed squared, minus the initial speed squared. And on this side, I still have F parallel multiplied by delta x. Let me multiply both sides of the equation by 2 and divide by m, such that on the left-hand side, I have 2 times the parallel component of the force divided by m times delta x is equal to the final speed squared minus the initial speed squared. F parallel divided by m, though, is equal to acceleration, because Newton's second law is F is equal to ma. So F divided by m is a. And as a result, here on the left-hand side, I have 2a delta x is equal to the final speed squared minus the initial speed squared. And so the final speed squared is equal to the initial speed squared plus 2a delta x. That equation of kinematics, which I derived to solve problems of motion with constant acceleration, is in fact an algebraically manipulated expression of the work-energy theorem.